record on this computer. And we are recording. Okay, so in the event that my electricity flickers, I will get kicked off of here, and you're welcome to hang out. And I'll have to log back in and everything. It probably will take a couple minutes. But in the event that it busts and it doesn't work, I will work some of these out on a video and post them. I can do that regardless with all my free time. But I'll try. Sorry. Let me finish writing this out to go back and forth between them. So $11 a meter. So how much of each type of fence? And what is the minimum cost? Minimum cost. So the minimum cost will be a dollar amount, and then $26 fence, and then $11 fence. Okay, so let me switch from here to here. Not there, here. Okay. Maybe. Oh, hello. Okay. So based on, this is a guided learning, and based on that guided learning, just daggone ding dong bell. Here's the picture that I came up with. There's land, there's rectangular, 74,000 square meters of land in a rectangular shape. The fence along the front part of the land. So this is front part of land. This fencing is going to cost, it's the fancy fence. It costs $26 a meter. And the other three sides, the cost is $11 per meter. And the question is how much, like how many meters of the expensive fence can he buy, and how many meters of the cheaper fence can he buy? And then what will be that minimum cost? So I don't think, no, the question itself, nope, I don't know if you can see the title of the questions when they show up, but this one is called minimizing the cost of a fence. So the thing to note here is that we're minimizing cost. So we have to come up with a cost function, and that cost function is what we will, as long as we have one variable, then we can take the derivative, find its critical number by setting it equal to 0, and we'll find our length. So for this, it's a rectangle. So, and again, this is really like the hardest part of this entire section, is your ability to come up with the equation. So I'm going to make a cost equation, and basically it'll be $26 times however amount of fence we'll need, plus $11 times whatever amount of fence is needed there. Like, I don't know what that is. You know, if you want to give it an X or give it a Y, if you want to give it a length and give it a width, it's really up to you. We can make it L's and W's. Pick your favorite letter. It's pouring down right. So like if this is a width, and this is a width, and this is a length, and this is a length, we still have to, you know, the two widths and the top length, all three of those measurements of meters will be this $11 area, or $11 perimeter. And then the 26 along the front will be the 20, that's this amount of fence, so the $26. So you can start replacing some letters if you want. Like it's $26 times the front length. Yeah, hope we don't lose power. 20, oh good Lord. Okay, $26 for whatever that front length is, plus $11 times whatever that width is, plus that length, plus that width again. Or if you want to, you can do 11 times, what is that, twice the width plus the length, something like that. Okay, but if that's, again, that's just setting up a cost function with respect to price times amount of fence plus price times amount of fence. okay? And I know a lot of people don't like word problems, so just bear with it till the end. The problem is there's two variables here, whether you use W and L or X and Y. I cannot take the derivative. We're not doing implicit in this section. I cannot take the derivative with respect to this right now. So what we did before is using, can you guys hear this ring? Using the other piece of information that's here, we've been given that we are working with an area of 74,000 square meters. So you'll use this other piece of information, use a given area of 74,000 meters square to write an area formula, write it in terms of W or L, and then we'll plug it back in. So I have an L, and I have a W, and I have another L. So as far as substituting and getting rid of one of those letters, what do you think would be the better choice? Like if I do area equals length times width, 74,000 equals length times width, should I do 74,000 over length equals W, or should I do 74,000 over W equals L? Which would be the better choice if I wanted to start substituting? Because that's what's going to happen, is we're going to take one of these amounts and plug them in for L or W, not both. But I have an L, oh my gosh, and I have a W and I have an L. Do you know which one would be a better choice to try to plug in for? I see a chat box. So if we choose the one over L, we're going to sub in for the W, and there's only one W. So Brianna, I think that would be a good choice. You could do the other one, but you would be replacing two parts of the equation, and I think it would get a little harder with the substitution. So if we don't do this one and we go with this choice, then it's a straight substitution. Okay, and if you want to, we can, where'd my thing go? We can distribute this so it's not 26 length plus 22 width plus 11 length. We could sort of combine like terms. 26, no, just kidding. What's 26 plus 11? 37? That would look better. We can take this 74,000 over L, and it's a substitute, like some substitute. Yeah. We're going to substitute that quantity for the W, because we can't take the derivative of 37L plus 22W, because we don't know what we're taking it with respect to. There's two variables. So if we replace one or the other in terms of the other, then what we have is this cost function that's this 37L plus 22 times 74,000 over L. And I know it doesn't look the best, but that is an equation that, oh, you can't see that because this is here maybe, I don't know. You have to tell me if you can like not start hearing things or seeing things, because it is pouring down rain here and lightning and thundering here in the Wilkesboro. But now you have a cost function that has one variable in it. Okay, and I don't have much more room, so I'm gonna have to go to a new piece of paper. Let's see, copy. I know they're excited it's raining, like they've never seen rain before in their life, right?
Open up the windows.
They're special. Okay, so here we have a cost function. Let me make sure we're, okay. So we have 37L, 22 times the fraction. You can just do the 22 times the fraction. I mean, the number's about to get really large. 74,000. Holy moly. 1628000 over L, which is the same thing as 37L plus 1628000 L to the negative 1. And that is a couple of power functions, and we can do power rule and find the derivative really easy. So here's a cost function. in terms of the length of the fence that we're going to use. And you have to take the derivative, set it equal to 0, and find the critical value, and that'll be your length. Okay, so I'm going to pause. If I need to go back and explain anything, now would be the time to say something. I'm not going to repeat the whole thing. You can watch this lecture again if you need to. But we had to create a cost function and then plug in variables that we could use based on what we were given. Don't see a chat. Okay. So now if we find C prime, it's the derivative of the cost function. We can do the derivative of the cost with respect to length, and we'll get the critical values, depending on what there are. I mean, we get length of land. If we get something negative, it's not a useful number. If we get 0 for land or for length of a fence, 0 is not a useful length for the diagram that we have. So if I do the derivative of this function, again, we're just using power rule for derivatives. Then the derivative of the cost with respect to length, or C prime, whichever one you want to call it, would be 37 plus, power rule says you bring the power down and you multiply it and then you subtract 1. So that's like 1,628,000 times -1. So that's -1,628,000. And then that gets raised to the -2 power. Then you have to find where this equals 0. So the -2 power really, oh, hello. Is it dinging again? No, maybe somebody left. I don't know. Turn my sound off, but then I can't hear you. That would really be the same as 1,628,000 over L squared. And again, we're trying to find critical numbers here. So I only see one L that you could solve for, and there's a couple of ways you could address this. I mean, you're not going to have a length of 0 for a perimeter on a rectangle. So even though it could be considered a critical number, it won't be helpful here. The other thing you could do here is maybe add that negative term to the right side, multiply to get, I mean, you have to solve for L. So however you understand how to do it, you could make a common denominator here if you wanted to, right? You could do L squared, so that you would have one common denominator. I'm so afraid I'm going to forget a 0. And when you have a single fraction, then you focus on what makes the numerator 0, what would make the bottom undefined. So the focus is here. So if we set 37 L squared minus that million number equal to 0, I'm going to add that over, divide the 37, whatever that is, 44,000. Well, look at that. And then square root to solve. I get a length of approximately 209.762 meters. And it's, I mean, the 44,000 square rooted, I mean, you could simplify it. I think it said to round 4 decimal places. Everything's to 4 decimal places. 4 decimal for the fence amounts and round up. That's a really stupid thing to say. It says use 4 decimal places for the fence amounts and round to 4 decimal places. Okay, so 4 decimal places. So maybe I should go 7618, whatever. Okay. But all I did is take the derivative of the cost function, set it equal to 0, pumped in some algebra I made a common fraction, set the numerator equal to 0. I mean, there's another way you could have done that, but this is what you get for length. It's really plus or minus, but we are not concerned with a negative 209 meter fence because that would be in another dimension and we wouldn't use it. So we're only going to use the positive square root here. We were asked to find how much of each type of fence would you need. So we would definitely need, so the length, to go back to the picture, the length is that front part that was 26, but you also need that much in the back, and then you have to figure how much of the width that you need. So if you use this information, so again, here's the picture. This costs 26 per meter. These three cost 11 per meter. And right now, this side is 209.7618 meters. So I definitely know for sure that I need 209.7618 meters of the expensive $26 fence. Like that's one of the questions. It's probably like the first question, okay? The second question is how much of the $11 fence do you need? So whatever it was, I need 209 across the top, but I also need however many meters the sides are. So you need to find the width. And gosh, this thing don't go. Welcome back, Riley. You would use the fact that the area was times width to give you 74,000, and we can plug our length that we found back into this formula, and it'll give us our width. So if we know, let's see, do this here, that 74,000 over length gave us the width, then 74,000 over this 209, whatever that is, I'm going to do 74,000, 3 zeros, and divide it by that answer. And that gives me a width on this property of 352.7812 meters. Okay, so that's the width part. So this width is 352.7812 meters. This length is 209.7618 meters. And this width is also $352 or 352.7812 meters. Okay, so again, get some color going. 209 meters of the $26 fence. And then for the other ones, we have, let's go green. This width, this length, all three of these added together will be the amount of the $11 fence. That's this fence, I swear. Whatever those three, you can do that. I don't need to add those up. Whatever those three are, that is what the sum for those should be. Okay. I mean, we could do it really quick. If I double that and then add that answer. Oh, syntax error, whatever. Why are you, okay, clear. I don't like this calculator. 352, I'm just rounding just to get a ballpark. What the heck? Whatever that symbol is. I missed my calculator. It's in my office. I'm not allowed to go back there. 913 or so. Once you add them all up, but you got to keep 4 decimals. It's like 913 meters. Again, you can add those 3 numbers up. I'm not going to add them up for you. But that's the meters of the fence. And then the final question was, what is the minimum cost? So you know that cost function that we came up with here? Let me get a highlighter. This guy, you take your length and your width and you plug it into that cost function, and that will be your minimum cost. It should be pretty simple for that one. To get the minimum, this minimum cost here, you just plug in L and W that you found into the cost function that we made. And I think it ends up being like somewhere around $15,000 for that one. Again, this could throw different numbers at you and different prices of fence, but the process is still going to be the same. The area might be different and the fencing might be different, but the process is the same. So that's a fun guided learning question. That's basically like a homework question. Yeah. Questions, comments, chatting. How did I make the cost function? Okay, so the cost function here was just the acknowledgement that we were doing $26 times however long the front fence was, plus $11 for whatever the other 3 sides were. And we'll do another cost function. I have one with the cylinder can to talk to you about if we Or maybe I'll let you try it since we did this cost one, because they're kind of the same thing. But it's a dollar amount times a physical amount, like a dollar amount times a meter representation, and a dollar amount times another representation. Does that make sense, Brian? Okay. I'm telling you now, start your homework, because you are going to need some time to process how to come up with some of these equations. Like I can't shout it loud enough on a tall enough soapbox to explain this to you. You need to start it. Okay. Okay. So, Tori, I hope that helped. And Olivia, you both said that you were stuck on that one. Let me make sure. Okay. Nope. Got another chat. Okay. There are, let's see, this one is not, these are just examples that I had on a thing that I posted. Here's the one that we did yesterday, which is kind of like what we did, but not, I don't know which one was harder or easier. Maybe the cost ones are harder. So this is the one that we started talking about at the end of class yesterday, where you were minimizing cost for a cylinder shape. And it gave you the capacity, which is another word for volume. So you're given the volume, but you're asked to minimize cost for surface area. So this is very much like the problem that we just did, but your shape is different. So the function that you have to come up with is sort of what I wrote up here at the top. It'll be the cost of whatever surface area are those top circles plus whatever cost that, it's like a soup label is what I like to think of it as, the cost to produce that shape. And so you have these pictures that are given to you, but I went ahead and wrote down the surface area formula for a cylinder from the geometry world. The 2 pi, again, surface area is the area of a surface, and it's a squared unit. So if you have a cylinder, the top and the bottoms are circles. The area of a circle is pi r squared, and there's 2 of them. That's why it's 2 pi r squared, top and bottom circle area. The lateral surface area, lateral means sides, that's the surface area. Again, if you could imagine, I know you all know what a can of soup is. Not a bag of ramen, actual can of soup. If you took the label off, it would be a rectangle. And that rectangle's area would be 2 pi r, that's the circumference of the circle, times height. So if you add those 2 things together, this is area of the top and bottom circles plus the area of the rectangle piece. That's kind of like a label. Again, that's how my mind processes that middle shape if you were to flatten it. And that's what this picture here does, is it shows you what that shape would look like if you cut it apart and laid it flat in 2 dimensions. Okay, so what you're doing is you're minimizing cost, but the cost depends on the surface area of the things that you're trying to cover. You're trying to cover the circles and you're trying to cover the middle. And anytime it says, what does it say? You're producing a container, you're trying to do material. Anytime you're trying to use material on something, that's a surface area. Anytime you're trying to fill something with a capacity, that's volume. So you're given the volume that it will hold, and then you're told that you're trying to minimize cost based on surface area. So the way that we come up with this cost equation for this whole thing that we're trying to minimize is it's 6 cents per side. Where did it go? The top and the bottom, I'm reading the question here. The top and the bottom of the container are made from material that costs 6 cents per square centimeter. So 6 cents times the surface area of the top and the bottom. Okay, so whatever surface area those circles encompass, it's 6 cents a square meter. Okay, plus, get another color here. The side of the container is material that's 3 cents per square centimeter. So then you have 3 cents times the surface area of that middle piece, that rectangle shape. So that is where surface area formula comes in for these pieces. So it's 6 cents for the circle pieces. And I am out of room. Wish these were bigger. Can I move you up some? Let's go here. So our cost function is 6 cents times 2 pi r squared plus 3 cents times 2 pi r h. Okay, that's the start. And if you can't build that, you will not get this question right. You have been warned. But anytime you are doing a cost equation, it is the price times the amount plus the price times the amount. Whatever prices you've been given, it's always price times amount. I mean, that's what cost is, right? If you want 10 bags of chips and each bag costs, it's price times amount, price times amount. I mean, that's just how you're going to get a cost function, okay? So with that being said, pi is a number. And when you go through and look at your variables, the problem is you don't know the radius or the height of this shape. And that's two unknowns, and that's a problem. So that is where you're like, oh, what else did they give me? And the other thing that they gave you was the fact that it would hold 1,000 cubic centimeters. So that is a volume, and you are told that the volume is 1,000 centimeters. So you can solve this volume formula for R or H, but it would make more sense to solve it for H, especially if you look at there's an R, there's an R, there's an H, just like before. If the H weren't there, it would be fantastic. So you could say that 1,000 over pi r squared is H, and we can plug that in for there. And then it gets crazy with some algebra. But it's the setup that I would like for you to see if you have questions on to start this one. Because then it's just going to turn into a couple of power functions with the power rule to find the derivative, which I feel like you should be pretty comfortable with at this point. But it's the equation building that is going to be the hard part. Would you multiply 0.06 pi r squared by 2? So Seth, the 0.6 pi r squared, are you asking, is that where the 2 came from? This would be so much if you guys would just
So like the 6 cents times the 2 pi r squared, is that the cost for one circle or both of them?
No, the 2 pi r squared is the top and the bottom. You're right. That's why it's already doubled. You wouldn't double it again.
Oh, okay.
Yeah.
Cool. Thank you.
You're welcome. Anybody else? So again, we're going to substitute a height equation from our volume that we were given, just like we did before with the area that we were trying to use, or yeah, the 74,000 for the fence area. I mean, you have a lot of information and you have to sort through what to do with it. So, you know, build the function that you're trying to optimize, then look at the other information that's given to you, and it will be used somewhere. Rarely have I seen any of these questions where it gives you an a not useful number at all. Okay, so with the the setup is what is sort of the harder thing here, and I'm trying to see if there's a fence, there's one. Okay, because I want to make sure I get these point questions in with you too. And it's 1:30. Okay, we're good. So if I do this cost equation, if I can capture it, because why did it do that? Copy. I've clearly run out of space. Paste. But I don't need all of that. I just want this guy. Okay, so we decided that we would replace H with 1,000 over pi r squared from the fact that our volume pi r squared h was 1,000. Again, I know you have it, but pi r squared. Okay, so we're replacing it from that. So this, it's multiplication. So 0.06 times 2 times pi times r squared. Come on, solar. This would be 0.12 pi r, I'm just combining. 0.03 times 2 is 0.06 pi r times 1,000 over pi r squared. Okay, so I'm combining what I can, and now I'm going to clean up what I can before I start to do any kind of crazy. The majority of these derivatives are not hard. In fact, a lot of them are power rules, but you have to do a little bit of algebraic cleanup first. So like on this one, you see how there's a pi and then you're dividing by a pi? Those can go. There's an r and then you're dividing by an r squared, so one of those can go. So here is the cost function that we're really working with. 0.12 pi r squared plus 0.06. Well, actually, what's 0.06 times 1,000? Is that 60? Yeah, 60 over r. That is the function that we're working with. And I'll put a 0 in front of that, so I don't lose the fact that it's a decimal. That's the function that we're minimizing. Are we minimizing? We're minimizing, yeah. So this is the simplified cost function that we need to minimize or optimize, or in this case, we're minimizing. So we need to take its derivative, find its critical numbers, and odds are there's one that works usually. I do have an example where there could be a couple depending on what the scenario is, but we will probably not get to it today. But we take the derivative of this function. It is a simple power rule of each of the pieces. You don't have to make a common denominator and try to do quotient rule and any of that craziness. It's just power rule, okay? 60 over r could be rewritten as 60r to the negative 1. So if I do, again, you could either do C prime or this Leibniz notation of derivative of cost with respect to radius, so you understand what it is that you're taking the derivative with respect to. Again, it's not implicit. Pi is just a number. So this is power rule, where we bring the 2 down and multiply it. Is that 0.24? Question in my math skills today. 0.24 pi times r. And then the plus 60r, that's another power rule. Again, we're just using power rule twice. So we'll bring down the negative 1, making it negative 60, and r gets a negative 2. And that's what we need to find the critical numbers for. So you can make that 60 over r squared. This looks a lot like the formula before. You do have the r in the denominator. A critical number could be 0, but you're not going to have a cylinder with a radius of 0, or you won't have a cylinder. Okay, it's just like when we did the square and the sides. If it was 20 on the side, you can't cut 10 because then you won't have a box. So even though it could be a critical number, it's not going to be anything important to help us minimize this. We can make it a common denominator of r squared so that we get 0.24 pi r cubed minus 60 over r squared. Again, an r value of 0 will not be applicable for this question, even though it's considered a critical number from the earlier sections of chapter 4. R equals 0 is useless here. So the focus will be what makes the numerator 0. So if you set 0.24 pi r cubed minus 60 equal to 0, add the 60, divide the 0.24 pi, and then cube root it, right? Oh, I need to get rid of the pi, sorry. Divide that guy over. So again, I just added the 60, that says 60, divided the 0.24 pi, and now we have r cubed equals, 60 divided by 24 might do something It says it's 250. 60 divided by 0.24 is 250, by the way. So we get r cubed is 250 over pi. If we cube root it, you get a radius of the cube root of 250 over pi. And that's exact, and I think that's what Sapling wants. I could be wrong, but I'm pretty sure it wants exact for this one. Otherwise, if you do 250 over, where is pi in this? There it is. And then I don't even know how to do cube root. How do you do cube root? Nope. 3 cube root. It ends up being like 4.3 or so on the radius, 4.30 if you do the decimal for it. But I think you have to give exact on your homework. That's straight algebra with some pi thrown in. Math pi, not real pi. That might be more fun. I don't know. Yeah, that's the radius. And I think the question asked for the dimensions that would minimize it. So that's your radius, because it's a radius and a height. That's what you're looking for. Once you have radius, you can stick it back into this height equation. The 1,000 over pi times radius squared. And I would bet Sapling takes that. You can simplify it, but it's a lot of algebra. You square the 250, you square the pi, and then you cube root it, or raise it to the 2/3 power, however you'd like to do it. I'd be okay with that, or a decimal approximation. I know Sapling will take it. I would be shocked if they didn't at this point, using this book for a year. But those are the dimensions. And if it wanted you to give the minimum cost, then that meant that cost equation that we had here, you would just plug the radius and the height back into it as exact as possible and give the cost to the nearest cent, however much it would cost for that to do. But it's real heavy algebra. The derivative of it is the easiest thing that you could probably do, but building the equation and then finding that critical number when they have to be exact, I'd start your homework is all I can say. It is strongly suggested that you do this. The sooner the better. Okay. I want to show you one more before we go. I mean, I have several, and I can post answers to a lot of these if you just want to watch or see if you can follow the math. Here's another cylinder one. This is the one I wanted to show you that show up in this section. So there's this one. Oh, crap, you don't want to do triangles. Maybe you do. Here we go. So one of the optimization problems that we look at is minimizing the distance between a point and a curve. And then the other one that shows up in this chapter is taking this wire and cutting it. And this one is going to use that concept of absolute extrema, where you had to consider endpoints. Remember, we did that back in section 4.2. So we'll probably get to that tomorrow. But for now, I would like to minimize the distance on a graph. So the idea here is you have a parabola, y equals x squared. You have a point randomly, and you would like to minimize, you want to know what's the shortest distance between that point and that curve. And you cannot look at a graph and find it, okay? It's not exact. Oh, wow. How can I get rid of all of that at once? We did trig earlier today. So here's x squared. Here's the point 2. I swear if my brain worked half the time. 2.5. So here we go. This is what we're trying to do. Somehow there's a distance from that point to that curve, and we're trying to find what is the shortest distance, the straight line. So what's the shortest distance? Like, where's the point? Come on, purple curve. Which point? Is it this point? Is it this point? Is it this point? You can use calculus, which is what we're going to do, and optimize a formula and find the point that would represent the shortest distance from that point to that curve. And again, I don't want you to like, sometimes you can see it on a graph, but usually you can't because it's this weird point. So there's a process for it. But that's what we're trying to come up with, is what's the point on this curve, the XY point, that would be the closest to the given point that they gave you. So how many of you remember distance formula from whenever they tell you that now? I don't even know where that would be, I'll be honest. Distance formula for the distance between 2 points. I know you have it in high school geometry, if that's math 2 at this point. You don't have to memorize it, I'll give it to you. You don't have to, I swear. But maybe you remember it, like if you had point 1, point 2. Here's the distance formula. It was the application of the Pythagorean theorem, right? It took the distance between the x values, the distance between the y values, squared them at, it was Pythagorean theorem if nobody ever showed you that. That's where distance formula comes from, is Pythagorean theorem on a triangle. But it took the x's and squared them, and it took the y's, squared them, added them together, took the square root. That's how you got the distance between. I swear you have this in school. I mean, math 2 maybe. I don't, maybe it's in middle school, but I can't imagine. But math is different now. But that is the geometric distance formula between 2 points on a plane. Okay, so the way we're going to do it is we're going to keep this x and this y as x's. Buddy, I'm almost, okay. Not right now. Keep that as x and y. And then for these two, you're going to plug in the point that you've been given. So here's what that looks like. X minus 2 squared plus y minus 1/2 squared. Okay, we're keeping the first ones as x and y's. We're plugging in our given x, y point that we're trying to minimize the distance with. And that is your distance formula. And that is a problem because it has an x and a y in it. And there's a square root. So if we kept this function as is, we can't do the x and the y. So what we can do here is we can replace, that is just a weird color for a highlighter. Let's go blue. We can take and use the fact that y equals x squared, and we can replace the y in our function, in our distance formula. So then we have x minus 2 squared plus x squared minus 1/2 squared. See how we just replace that? We just replace with the function. So replace with the function given. And now we take the derivative of the distance formula with respect to x. So here is my question to you, and I know we're running out of time. That is not a nice formula to take the derivative of, because guess what you would have to do if you did it the way that it looked right now? If you had all that crap with a square root on it and you wanted the derivative of it, what would you have to do? See if anybody wants to chat. Mary Grace says chain. You would have to power it and then chain that whole piece inside. And do you know how not nice that would be? Okay, so what I'd like to show you is the same formula without the square root, which I know they're two different formulas. They're two totally separate formulas, right? One has a square root, one doesn't. But I would like to show you, and then we'll stop for the day, that minimizing either one of those gives you the same number. So I want to show you that on a graph, even though I don't want you to use a graph a lot. I just like to show, I'd like this to be a showing time. So x minus 2 squared plus x squared minus 1/2 squared. I think I did that right? Okay, so there's the minimum for that one. It happens at 1. Okay, if I did the exact same thing, but without the square root, x minus 2 squared plus x squared minus 0.5 squared. Did I do that right? Yeah. Yeah. So I would like to point out, trying to do this so you can see both at the same time. I don't know if you're going to be able to. They both have minimums and they both occur at 1. Do you see that? So whether we use the square root function or the one without the square root, if we minimize it, we get the same number. So we, for sake of sanity and doing derivatives, we're going to use this form to get the derivative because it's nicer than the square root. And we can because whether we minimize one or the other, you get the exact same thing. Okay? So the one on the right is much nicer to do the derivative of than the one with the radical. And you can take away the radical because both functions minimize the same way. So I wanted to show you that on a graph. You do get 1. That's going to be the answer. But I need you to do the derivative and we'll find that it's 1. But I just wanted to show you that on a graph that whether you do the square root function or the one without, that they get minimized at the same value. Their minimums are different, but the value at which they minimize are exactly the same. So we can do that one more tomorrow, and the one with the wire, and maybe the other, however many of you that haven't started your homework yet, the other 17 of you that haven't started the guided learning, you probably should. But I'll pull all of the annotated things that I have for this and try to post them, because right now I think it's just the blank one. And we haven't done all of them that I had on this handout, but I think I have annotated for most of them. So I'll try to post that, but we'll talk more. It's full of word problems, but it's you have to know what formulas to use. The distance formula one you'll be given, the geometrical formulas you'll be given them. You won't have to memorize them, but you still have to know what to do with them. Yay. When are we ever going to have to use calculus to optimize word problems? There you go. Which is a required part of this course to get the degree that you've chosen from Appalachian State University. Okay, do you have questions? Some of you just need to have some one-on-one calculus time. You need to sit down, no distraction, try to start it, go back through what are these called? The lectures if you need to. I'll try to have this one posted by 2:30 or 3. And just let me know if you have questions, okay? Glad you came today. You missed a lot if you didn't. You have to go back and watch it. Start your homework if you, you should start it, but make some time for it. Please email me if you have questions. If you want me to check your setup, snap a picture, send it to my email. I'm happy to look at it. Just make sure it's in a form. I can't do, there's only a couple of you that I ran into issues with the quiz with the HEIC, the newer iPhones. I can't pull those image files up. But otherwise, just let me know how I can help you. Okay? And I can't see any of you, so I really feel like I'm talking to myself, but that's okay. We'll see you tomorrow.